So good, appropriate local time of day to everybody. I'm very excited to be here today to introduce today's high contrast imaging theme by telling you a bit about detection and characterizing by high contrast imaging of exoplanets, in particular, the promise of the mid-infrared. And I'll just kind of, my slide is a bit of note to this here. Obviously, this is a planet that we know very well. What's exciting about direct imaging is that in the long term, it is a technique that's going to be very sensitive to similar planets, so exo-Earth twins, planets about 1 AU away from G stars. But that's not the only reason that direct imaging is a key technique. So one thing as a direct imager I get all the time is, so we have thousands of transiting exoplanets and hundreds of radial velocity exoplanets, and you only have maybe about 20 directly imaged exoplanets. Why should we care? So I gave you one example, right? So eventually this is going to be a very key technique for detecting exo-Earth twins, so habitable zone planets around G stars. But in the shorter term, direct imaging provides important tests of planet formation theories. We're mostly imaging younger planets, some that are in the midst of formation. So forming planets obviously directly gives us constraints on how they formed. And the other is with photons directly from planets themselves, we can really probe their atmospheres in detail via spectroscopy. We can also determine masses, especially in combination with other techniques, and rotations, a lot of other measurements we can do. So there's a real fount of knowledge we can gain about the physical properties of these planets. So here are some examples of the 20 or so directly imaged exoplanets we have to date. I'm not going to give it an exact number because that number is also changing, and different people in the field also have different opinions as to what should go in that cohort of objects. But the first of these were detected about almost 15 years ago now. HR 8799 BCDE and Beta Pic B. So these are planets more massive than Jupiter. You're looking at images in the near infrared because this is where the contrast ratio between the star and the planet is most favorable for these relatively warm young planets. Since these initial detections, we've now had kind of a second generation of discoveries with dedicated planet finding imagers, such as the Gemini Planet Imager at Gemini and Sphere at the VLT. And I'll in particular point out this planet on the bottom right here, two planets rather, PDS 70 B and C. So these are actually protoplanets embedded in a disk. They're still accreting. Again, this gives us direct probes of planet formation. So to recap, right now, the planets that we are imaging are essentially what I like to refer to as baby Jupiters. They're actually more massive than Jupiter, 3 to 20 Jupiter masses or so, relatively warm, 600 to 1400 Kelvin, especially compared to solar system planets, and young. So in some cases, they're all close to the epoch of formation, but some are still in formation. We detect them at separations of tens to hundreds of AU from their stars, and at contrast of 10 to the 4th to 10 to the 6th with the star right now. Right now, this has mostly been in the near infrared using 8-meter ground-based telescopes plus adaptive optics and coronagraphy. And in fact, from this cohort here, there's only, all of these are near infrared images except for 2 L-band images here. And again, this is largely because this is where the black body peak of these are. It's also where adaptive optics works well in getting us to diffraction limits, and we have chronographs to use at these wavelengths as well. But moving to longer wavelengths is going to be really key in terms of scientific return for these planets and lower mass planets. So this hasn't been done so much from the ground, certainly not beyond 5 microns because of the general problem of the sky glowing at those wavelengths. But obviously in the next year, we're going to start opening up wavelengths greater than 5 microns. They're inaccessible from the ground. And as you open up new wavelengths, you open up new physics, new molecules to look for, and just new probes of these atmospheres. And then longer term, you move to a longer wavelength, you're also moving to a cooler temperature for the black body peak of your planet. So that means the mid-infrared gives us sensitivity to older, down to solar system ages, with ELTs and lower mass planets as well. So we're going to see rapid progress with this in the next couple years for the obvious reason, right? Which is JWST is now in orbit, and we're all, I'm sure everyone on this call is super relieved that we're through launch and commissioning has begun very uneventfully. So longer term, ELTs with instruments such as METIS at the European ELT and other similar instruments will also open up longer wavelengths at higher contrast and higher resolutions as well. So I'm going to just kind of go through these two themes again and give you some examples of what we get from opening up longer wavelengths first, and then I'll come back to older and lower mass planets. So to orient you first, before we can talk about what we'll learn from longer wavelengths, I need to tell you a bit about what we know about the atmospheres of young giant exoplanets from the near-infrared studies done to date. And to do that, I also need to go back and talk a little bit about brown dwarfs. So brown dwarfs are the higher mass cousins of directly imaged exoplanets. They're older and same temperatures, but just more mass packed into about the same space, and hence their higher surface gravity. Brown dwarfs, of course, just cool with age, and you start out with an L brown dwarf. This is this sequence here, these gray triangles, and they're very red. And that's been attributed to silicate clouds in their atmospheres, mostly just that's the easiest explanation for these red colors. And as a given object cools over time, eventually these clouds break up or fall below the photosphere, and you move to this bluer end of the sequence. These are our T dwarfs. And at this point, you also get cool enough that methane starts to dominate over carbon monoxide in the molecular features detected in these atmospheres. So before the detection of beta PIC B and HR8799, we assumed that our young planets should all look like T dwarfs and have strong methane absorption. And what we found is that was very much not the case. Young planets imaged to date, as well as similar free-floating objects in the field, of which we also have tens, are very red. So they almost are entirely along this L dwarf sequence, even though in some cases they have the luminosity you would expect if they were T dwarfs. In fact, only one so far has robustly shown this methane absorption feature at 1.6 microns that we were very much expecting from this whole class of objects. So the easy explanation here is clouds. It's the same silicate clouds for the high surface gravity brown dwarfs as the low surface gravity planetary mass objects. But remember, our evidence for this is indirect. It's just based on the red colors, and there are some other possible explanations. So there's the clouds, but there's also models that use non-equilibrium chemistry and vertical mixing to produce the same red colors, and also thermochemical instabilities to further drive that vertical mixing. And here is an example of a spectrum of one of these young objects. So PSO 318 here in red is a young free-floating planetary mass object with an estimated mass of about 8 Jupiter masses. And this is a cloud-free model with thermochemical instabilities that can very well reproduce this spectrum and its red color without clouds. So mid-infrared may have the answer for this question, whether or not you have clouds in the atmosphere. And honestly, probably the answer is yes. But again, our detection is indirect. It would be nice if we could directly detect these. And again, we look towards brown dwarfs for how to do that. So on the right here, these are Spitzer spectra for L-type brown dwarfs from Cushing et al. 2006. And if you look in the mid-Ls, there is this plateau feature instead of a sloped feature here, which Cushing et al. Attribute to small silicate grains. So at least for the higher mass brown dwarfs, we do seem to have direct evidence of silicate grains in their atmospheres. But what about for young giant exoplanets? This is something that we're going to actually have an answer for probably in the next year, which is pretty exciting. So there are GTO and early release science programs that will definitely be probing this wavelength regime, both for brown dwarfs and young giant exoplanets and free-floating planetary mass objects. But in general, it's not just this particular feature. Longer wavelengths provide more stringent tests for model atmosphere predictions. So this is looking from 1 to 5 microns at spectra of 2 of the HR8799 planets and 2 mass 1207b. The details of these different models is actually not super important. These are different thick clouds and non-equilibrium chemistry models. The key things here is if you look at the model predictions at shorter wavelengths, there's not a lot of variation between these different models that have rather different physics in them. If you move to longer wavelengths, you can distinguish between these models in a lot more detail, especially if you can do spectrophotometry or spectroscopy and really get better wavelength sampling. You can actually select between these different models much more effectively at longer wavelengths versus shorter wavelengths. And in terms of beyond 5 microns, what exactly we're going to see and how well we're going to constrain models, that's actually still, I can't honestly tell you what we're going to find, but I'm pretty excited to find out in the next couple of years. So that's just a bit of a flavor of what you get from opening up longer wavelengths and what sort of physics you can probe with that. The other part of the promise of the mid-infrared is to be able to push down to detecting and characterizing older and lower mass planets. And to do that, going back to models again. So this is the absolute magnitude of an 8 Jupiter mass planet just from the BROF 2003 models, looking in a range of wavelengths, so near infrared into the thermal infrared. So a little bit of a confession, this is a fairly extreme model in terms of the difference between the mid-infrared and the near-infrared. So this is a hot start model where the planet starts out very large and puffy at early ages. There are also cold start models which start in a lower entropy state. But common to all of these models, although they vary by degree, the mid-infrared, longer wavelengths remain brighter at later ages compared to the near-infrared, which really decays quite quickly, hence why we've been limited to planets at ages of less than 100 mega years so far. So this lets us push down in the short term, potentially to young Saturn mass planets. And I'm not going to, so these are some topics I'm not going to go into in detail because there are some talks coming up this session that will probably treat on this in much more detail. So Laurent is going to be talking about high contrast imaging with JWST, and Miri, especially in the mid-infrared, can push down to potentially quite low mass young planets. There's also a number of exciting mid-infrared and near-infrared interferometric AO projects that are going to, again, push down to lower mass, closer in planets. So there'll be several talks about that this session. And longer term, from ELT instruments and future space missions, we'll push down first to super Earths around nearby M stars, and then eventually to true exo-Earth twins. But this is actually probably going to fundamentally change what sort of planets we go after when we do direct imaging surveys of planets. The previous generations of direct imaging surveys assume, because we're working mostly in the near infrareds, there's a couple of mid-infrared surveys as well, that the younger the better and the closer the better. So stars have mostly been chosen for their youth and their proximity. But when we start moving to higher contrasts, we start being able to detect planets that have already been detected via other methods. So here's an example of radial velocity planets that will be detectable with METIS at the EELT. So up to 26 known planets will be detected that way. You can also combine astrometry, so absolute astrometry, Gaia astrometry. So some of the Gaia detected planets may also be detectable with METIS or similar imagers at ELTs. And Emily Rickman is going to talk about this more later this session. In the mid-infrared in particular, we may be able to push down to super Earths around nearby stars. So this is a simulation taking statistics from the Kepler mission, so the distribution of planets nearby, close-in planets around the very nearest M stars, simulating that, and then looking at what METIS would be able to image. And what you can see, we're not quite getting down to true Earth mass planets, but certainly super Earths down to habitable zone temperatures are quite possible. And one of the planets that we might hope to detect with METIS is in fact the nearest habitable zone planet. So this is just comparing contrast for a variety of next generation imagers. But Proxima Cn-b is probably a factor about 10 to the 7, fainter than its star, but you need to get very close in, about 20 milliarc seconds to do so. But this is the sort of planet that we might conceivably image with an ELT. And once we've done that, what might we expect to see when we start imaging habitable zone temperature atmospheres? So I want to conclude by just showing you actually the first habitable zone temperature object that we've imaged outside of our own solar system. So this is the coldest imaged atmosphere outside of our solar system. This is WISE 0855. It is a very low mass nearby brown dwarf. So it's only about 2 parsecs away, extremely faint, only detected so far in the mid-infrared. No matter what age you estimate from the system, the model mass from its luminosity comes out to be about 7 to 10 Jupiter masses. So actually truly a planetary mass object. And its effective temperature is below freezing, so 250 Kelvin. So right a little bit colder than the habitable zone, but pretty close. So here is its mid-infrared spectrum taken with Gemini from 4.4 to 5.2 microns. And obviously this is a very first cut spectrum. I think there's already a number of accepted programs to get better spectroscopy of this object with James Webb, but we're learning some interesting things from even this. So here is a comparison with Jupiter, actually a much colder object than this. And one key difference is WISE 0855 doesn't seem to have this strong phosphine feature that we see in Jupiter. Now, again, comparing just single objects, we really need to be able to compare a whole statistically significant sample to draw full conclusions here. But I'm hopeful that that's something that we will be able to do in the next 5 to 10 years. So for now, I think it's going to be moving to somewhat lower mass young planets with JWST, detecting RV planets, and maybe even some nearby super Earths with ELT METIS. But then eventually, I think with future space missions like something like LUVOIR, we are going to start detecting and characterizing a wide range of exo-Earth twins. And this is also where the mid-infrared becomes important as well. Once we have that sample of exo-Earth twins of habitable zone planets, there isn't one smoking gun biosignature that we can point to. Although I guess there's some people who would argue for phosphine, but maybe we won't get into that quite yet. So usually people look for non-equilibrium chemistry. So you want to cover as wide a wavelength range as possible and look for a combination of molecules you would not see if your atmosphere was in equilibrium, and that disequilibrium is evidence for life. And the mid-infrared is actually a very key wavelength regime to cover here to get that range of molecules. All right, so I'll leave it at that. I'll put up my conclusions. So essentially just going back to these 2 themes, why do we want to move into the mid-infrared? This is a wavelength range that's largely unexplored for young giant exoplanets right now, and exploring that in the short term is going to really help constrain our atmospheric models for these planets. And then in the longer terms, we're going to be able to push down to detecting and characterizing with direct imaging older, lower mass planets using the mid-infrared. All right, I'll stop there. Happy to take questions.
Great, thanks, Beth. It was a great talk. So while people is posting questions on the Slack, I do have a few, but I will start with one and then I will let the others to also ask questions. I was wondering, you started saying that we have very few of these planets detected. And I was wondering if this is because of the techniques or if it's more that intrinsically we expect to have less of these planets because of some formation mechanism. Do you have any theory, or is this being discussed?
So I do think that intrinsically we do know there are not that many giant exoplanets 50 to 100, well, even 20 to 100 AU from their star. We have, through several generations of deep direct imaging surveys, very strong constraints on the frequency of young giant planets. And in fact, it's a little embarrassing if you look at the yield studies for before the current generation of surveys with Sphere and GPI, where we were saying things like, we're going to detect 40 planets in this survey. And we were extrapolating from radial velocity planets because that's what we could use. That was the one distribution we had. And what we have found is, yes, from 20 to past out to 100 AU, there aren't a lot of planets, young giant planets. But we also know that from radial velocity studies now, that if you can push down close in enough, so once we start being able to probe from, say, 3 to 10 AU at great depth with direct imaging, we do know that there are planets to detect there. So I do expect the yield of directly imaged planets to really start increasing quickly once we start probing those separation regimes.
Great, thanks. Other questions for Beth? I do have another one. You know, people, if you don't ask questions, I would just ask all my questions here. So, so I have another one. I see that you are very excited about going to smaller planets and older planets. But what about studying, like, for example, protoplanetary disks around the young planets? Because I think this is the only technique that we have to actually make observations of these, which it will be really exciting to know more about planet formation. So do you think we can also push more into that?
Yeah, absolutely. And with that, also more wavelength coverage, the better.
Leo is asking, can you say more about biosignatures?
See, the problem is I gave you my observational astronomer version of who works mostly on direct imaging version of biosignatures. So my understanding of the field, which is not a deep understanding, is that again, that there still is not one real clear single biosignature gas that you would say, okay, we detected life, because almost everything, like ozone, for instance, has abiotic and biotic ways of producing it. So only the combination of various features altogether would be a really clear sign of life on a planet. Well, actually, maybe I should open it up to other people. Like there's was the whole phosphine detection on Venus, and there are people who very much argue that phosphine is that one smoking gun biosignature, but I don't know so much about that. I guess what I will end with that is that I don't think we're going to have a very clear detection of something we would consider life before we have detected and characterized on order 40 to 60 exo-Earths. Just because with just one, unless we have a statistical sample, we are not going to be able to really understand what our false positives and what our false negatives look like. Because, we can distinguish a Mars from an Earth from a Venus, but we just don't know the range of different exo-habitable zone planets out there yet.